Hello everyone. Welcome to a concept section for our video lectures. Okay, so today we're gonna dig a little deeper into uh, the fields, electric and magnetic fields, and the auxiliary field. This is the auxiliary field, and this is the displacement field. So auxiliary, and this is the displacement. Okay, so let's look at the laws first. So in the matter, these are relations between things. You have a polarization, so P is polarization, which is the density of electric dipole moment. So delta P, delta V, that's what it stands for. And M is the magnetization. And this is dipole moment over the volume. So the density of dipole moment, and those are both are density dipole moment. This is the dipole moment for the electric charges, and this is the dipole moment for the magnets. Okay, and so there we introduce various fields to write these equations more simply. You can write it in a more complicated way, but when you introduce this, it becomes much simpler. So of course, if the polarization is 0, D is just epsilon E, and there's no magnet, then M is 0 and H is just, so they're kind of related. But if there's a magnetization, they can be very different. For instance, H can be in this direction and the B will be opposite direction inside a magnet, for instance. If M is large enough, then M will overcome the B and it will be opposite. So H will be in one way and B will be another way. Okay. All right. So here we want to say, suppose we have two media, 1 and 2, and then what do these laws say? That there will be a relationship at the interface. So that's what boundary condition means. If I found something, let's say a point P at the boundary. So here's the interface, and so this is the interface, and there's a point P here. So above this, directly above this is say you have a E1, B1, D1, H1. Suppose you know that, and directly below that is E2, B2, D2, and H2. And the question is, are there a relationship between them? And those are called boundary conditions. And it's very useful actually in solving problems. Okay, as you will find out. So if you, for instance, if you knew this, then you can get these just by using the boundary condition. Okay, so let's work it out how these equations give us the boundary condition. All right. So I'm going to start with set number 2. I'm going to start with number 2. So I want to relate B1 and B2. To relate that, what I'm going to do is I'm going to think of a little pillbox that goes above, little pillbox, and then goes above and below. So you can see that, and this P is right at the boundary here. So suppose I had in this pillbox, when your del dot B, from del dot B equal to 0, if I integrate integrate over a volume of this pillbox, it still will be 0. But then you convert this, the left side is an integral, so dV equal to 0. This is the volume. And then this should be from, this divergence into volume will turn into a surface integral, a closed surface of the entire outside surface will be B dot n hat dA equal to 0. A is the area element, and maybe capital A, let's put it. Okay, so this is just a normal component. So this is outward normal component. So if I look at the top here, it will be, you can see from inside out, this will be n hat. This surface is 1, and then there is a surface other n2. This n will be n2 hat. And so what we'll get is this, say the area here is area is just A. So what I get is area of the edges, area of the edge, and this area of the edge. And then you have you go around here, the normal is that way. Let's call it surface number 3. So normal 3 will be that way. And what I want to do is this write out in surface S1 plus surface S2 plus surface S3 equal to 0. So the left side will be divided into 3 things. So this one is surface 3, and I want to know what happens not so far away from the surface. So this may be the height of the pillbox. There's h over 2 on the above and h over 2 below, and I want to take a limit h goes to 0. So this part, when I take that limit, this goes to 0, but this stays. So this one gives me B1. So this surface B dot n hat is, so this is B1 normal dA, and this is B2 normal dA. But this normal is with respect to this direction. But suppose I wanted to use the same direction. So say this was the z-axis, then this will be a minus that, right? So we're going to define the same as going outward z-axis. So this will be bz, and this will be minus b1z, and this is minus b2z. So it says the b1z has to be equal to, oh no, let's do the whole thing. So this will be b1z area at the edge minus b2z area of the edge equal to 0, and area of the edge is 0. So what we find out is b1z equals to b2z if the z was normal. Okay, whatever the normal is, we're going to take normal from not pillbox. We'll take the normal from going from this normal is the common normal. This, so that will be the normal, and so that gives this. So we see that the del dot things, if it's right side 0, it gives me right side 0, and that leads to this equation, right? So that's one of the, so B1 normal equals to B2 normal. So just the normal component. So this is one equation, one boundary condition we get. So let's try to do this one next. So doing the one next, you see you're gonna get the same thing. This will become a D. We do exactly same thing. This is D, and the right side is going to be the volume rho f dv. So instead of 0, this is going to be all the charge that's inside this pillbox Q enclosed, and this is d. So you're going to have d1, d2 with respect to this normal, with respect to n2 normal, and then if I take a z-axis, you have a d1z minus d2z, and this will again be 0, but this one will be Q enclosed on the right side. So what is a Q enclosed? Q enclosed the rho f and the volume. So this is the area of the end times the height. So Q enclosed is rho f times the volume, right? AE and height. So it says how much is the charge enclosed here. So if there is a surface charge, so is the volume, if there's a volume and then plus any surface charge times area E. So that kind of, when you do this integral, it's easy to make a mistake that if there's a surface charge, then we have to include that. So surface charge AE, and you can see when I do the H go to 0, this goes to 0, then this also goes to 0, but this remains. So now coming, I have this remain, and so we have a D here, D1Z AE, D2NC, and this is sigma a free charge AE. Now AE cancels out, so this is, the D's are not the same if there are surface charge right at the boundary. Okay, D1Z minus D2Z, and here the normal is going from 1 towards from 2 towards 1 is equal to sigma f. So that's number 2, d1n minus d2n equal to, this is sigma f is the extra charge you have placed. It's not coming from dielectrics, it's the extra charge you have placed, okay, on the surface. And now we're ready to do the del cross. So let's do the number 3. So when we look at a del cross, what we're going to do is, on this surface, we are going to take a loop, a closed loop. This is the one side, two side, and so this is at the surface. So this is some I go this like that. So we have a this is h over 2 and this is h over 2, and let's call it L. I'm going parallel, so let's call it parallel to the interface. So if I go around this and I do this as a so I integrate over this area and let the normal come in out here. This is new normal, not that normal. This is a new normal. So normal, now we have a 3 normal going on here. Oh, normal 4 type of normal here. Then del cross E dot n hat ds. This is a oriented area, and this is open area, so this surface is open surface, unlike the earlier one. And so on the right side is d dt b dot n hat dA, and I do the same thing over here. Okay, so this will be like a flux going through here. So the right side is going to be minus d dt flux of B, and this area is going to be eventually want to take a limit h go to 0 just before, so because interested in things happening at that point above and below. So what will this be? This will be simply go around this loop, and I use the right hand rule. If the n is that way, then I go around in this way. So A, B, C, D, and back to A. So A, B, C, D, back to A. E dot dl, and on the other side is minus d dt. Maybe you can just take a B at the above, B1, and this area, let's call it A over 2 plus B2 A over 1, and these A's and B's are parallel. This is parallel to the surface, but normal in that direction. So in that direction. So if say if this is called x, then this would be B1x and B2x. So if this was x, just for instance, just to simplify. But this will be perpendicular to x, so this will be like a direction that will be like a y. Okay, and so you will get so the y is this way. So just write down like that. This will be AB, A to B, plus B to C, plus C to D, plus D back to A on the left side. And on the right side will be this stuff. Okay, so when I take a limit, h goes to 0, this area is h over 2 times length parallel. So when h goes to 0, this h goes to 0, the right side goes to 0. All right, that's very interesting. The right side simplifies so easily. So over here, E dot dl from here is going to Ex. So this one, this Ex times L parallel, and B to C is, you can see it's going to be this. So this is the y, and x is that way. So it will be I'm going in the z direction. I'm going in the z direction, and electric field can be arbitrary point, right? So it's going to be like an EZ. So this will be EZ, and so this will be actually pretty interesting. It will be EZ 2 and H over 2 plus EZ1 L over 2. It's going to be like that, but when I got H over 2, so H over 2, this will go to 0, so this will go to 0, and D to C will similarly, this will also go to 0 as H goes to 0, and then C to D is the X component in the first direction, but I'm going in the opposite direction, so minus Ex of the first, this was for the number 2, L parallel equal to 0. And this actually L parallel is L along the X, L along the X. So we say E1x equals to E2x. This should be along the y direction, not x. This is the y direction, y direction, y direction, y direction. So when the normal was along the x direction, we formed this. I can take a loop normal along the y direction. So if I take a loop in the pointed that way, so that normal was pointed equals to j hat y direction or y hat direction, then using that loop I'll get E1x equal to E1y. As a matter of fact, I can loop any direction parallel to that, so any combination of this as a vector will give me E parallel vector. Any direction parallel of the two equals to let's call it 1, and E vector parallel to. So along the boundary, the parallel current point electric field above is same as below, just comparing the boundary. Okay, that's a very important result, because this is actually 2, right? So this is 1 and this is 1, but this has two conditions here, because this is vector, two-dimensional vector along the plane. Okay. Now, if you had a surface which is curved, then you are going to be over here parallel. So this, it will correspond to this direction. If you were over here, this will correspond to electric field along that direction, electric field along that direction. They will be equal to each other. So it's a pretty powerful, this is a very powerful way to use it. Okay, it turns out these two are very useful, right? So now we're down to the last one. Okay, so we do del cross again the same way for the fourth. We can do it on the del cross H, and for concreteness we take a loop which normal is along the x direction. Okay, which is I hat del cross H dot n hat dA along this loop A, B, C, D. AB is in the 2 and CD is in 1. It's kind of hard to draw, right? And I do over this area or surface. That's equal to JF dot n hat ds. This is the current enclosed. So basically, I have this. Now let me take a different pen, like this. This area, how much current is flowing through that area? You know, so how much total current? So if there is a surface current here, say KF, that's going to count, but all the other places current will be give me 0. So this will be K, whatever KF is, times this length over which on the surface is going to act L, what is called Y, because in this case as Y is going to be L parallel in general. When this guy, then you have a plus d dt in a dA. So if I take a limit, height go to 0, in that limit this h goes to 0, this will be 0. Okay, so just like it happened over here in earlier calculation. So I'm not going to repeat that calculation here, but it's going to be repeat that and same thing. So this is that. And so over here you say H, so along the Y, I first got the H in the 2, and which is H2Y Ly, and over here it will be minus H1Y Ly, and this is on the right side is going to be Kf Ly. So Ly kind of cancels out. So this thing shows that H2 parallel, and it's going to be vector, minus H1 parallel, that's going to be you can take a loop in arbitrary direction, and that's going to be Kf vector. So the over here the Kf was in x direction, and okay, so these are the boundary conditions. So even this is very useful, okay, in situations all over the place, to relate one place a form to the other place. Let's try to in next video I'm going to try to use these boundary conditions to talk about what is called magnetic circuits. Okay, so we're going to do magnetic circuits, which is kind of like a very interesting idea to think in terms of B flow, you know, B fields make a circuit, like they close loops, kind of like a current is flowing circuit. Nothing is flowing, it's just B field has to close in itself. Okay, so it turns out it's a good analogy to make what is called magnetic circuits. That's the next video. Okay, I'm going to stop here. This is a little bit theoretical discussion about how to relate to interfaces, and we are going to use this when we do like electromagnetic wave. In the electromagnetic wave, say you want to know reflection, say reflection of a then you will have some medium here, and you're going to reflect. So that's, you want to know which way is going to reflect. A wave comes in, which way it goes. So this will be some E and B, and then there will be in the back, say, refraction. So then there will be some back. So this is medium, say 2, medium 1 and medium 2, and the normal is from medium 2 to medium 1 in this equations. This is the normal from 2 to 1, and this equation. So you'll have a net electric field here based on this plus this. There's 2 waves here. So electric field will be combination of these 2 waves, and the electric field will be combination of these 2 waves. The electric field here will be same. The parallel component is the same. And then you look at the D, and if there are no charges here, then the D normal will be continuous. So D normal here equal D normal there. And same with B normal here is same with B normal here. So you will have an electric field, magnetic field. So we are going to use these boundary conditions when we study electromagnetic wave refraction, for instance. Okay, when you're going through the waveguide, we're going to use this to show the waveguide, how the waves travel through a waveguide. Okay, I'm going to stop this now, and I'll see you in another video. Bye.